Today we're going to show how an electronically commutated fan motor works and why it's more efficient than an inexpensive shaded pole fan motor. Now we've partially disassembled an electronically commutated fan, and electronically commutated fans are actually DC brushless motors, and they're generally outrunner type DC brushless motors because the motor coils sit in the stationary part, or the stator, rather than on the rotating part, or the rotor. Now the rotor of an outrunner type motor is a magnet, as you can see here. This particular motor is also what's called a four-pole motor because it has four coils. The way this works is that an electronic controller continually energizes windings, turning them into electromagnets in a sequence to keep the motor turning. The energized windings, of course, interact with the magnet in the rotor in a way that makes the rotor spin. Also, when we say these motors are electronically commutated, the commutation is the act of switching the electrical connections from one winding to the next one. Specifically, let's show one sequence as an example. To start out, one set of coils, say these two, would be energized to become electromagnets. Then the opposite poles of the rotor and stator are attracted to each other. As the rotor nears the energized coil, the next coil is energized. As the rotor nears that one, we're back to the first set of coils, and they're energized with the opposite polarity. So basically, you always have one set of coils pulling on the rotor. Now, I've explained this using only one set of coils at a time, but I don't want to give the impression that only one set at a time are energized. In reality, you energize this set of coils behind the set pulling on the rotor, so the other coils push on the rotor. So there's a combined effect of pulling and pushing on the rotor, which gives this motor a lot of efficiency. And high efficiency is one of the reasons you see fans built with electronically commutated DC motors. Now, to energize the right coils at the right time, you have to know the position of the magnetic poles in the rotor. Then, in other words, you have to sense the position of the rotor. An electronic controller reads a sensor to decide what coils to energize. The usual way you sense the rotor position is with a Hall effect sensor. It's also possible to measure the back EMF in the undriven coils to infer the rotor position, eliminating the need for a separate Hall effect sensor. But that scheme is a bit more complicated, and we know this motor uses a Hall sensor because we can actually see it. Brushless motors like this one are typically 85 to 90% efficient, largely because, as we were able to show here, most of the energy going into the coils actually moves the rotor. We can contrast this type of motor with another type found in fans, the shaded pole motor. A shaded pole motor is a type of induction motor. The reason it's called an induction motor is that if you recall the rotor on the DC brushless motor, it was a magnet. But you can see the rotor on an induction motor isn't a magnet. Instead, electromagnets in the stator induce magnetism in the rotor squirrel cage, as it's called, hence the name induction motor. Now, the name shaded pole comes from the use of a small winding in the motor that is affected by the induced magnetic flux. It's a bit tough to see on this motor, but if you look in here, you can kind of see this small break in the laminations. That's the shaded pole. And some shaded pole motors don't even use a winding, they just use a break in the laminations. The principle of operation in the shaded pole motor is that current is induced in this small winding from the main part of the winding. The current produces its own flux, which opposes the main flux in the motor. If you consider the magnetic flux in the main pole and the shaded pole, there's a time and space displacement between them. And this time and space displacement shifts around the stator at roughly the same rate as the AC line frequency. And it's this shifting or rotating electric field that gets the fan motor spinning and keeps it spinning. Now, the nice thing about shaded pole motors is that they're inexpensive because they have a pretty simple construction. But the problem is they're inefficient. Figures I've seen put the efficiency of the shaded pole motor at only between 15 and 30%. It's probably okay if you only have one fan, but if you think about an application like a data center where you've got racks and racks and racks and racks of servers, and each server has its own little fan, you just don't want hundreds or even thousands of fans operating at only 30% efficiency. So that's where you really can benefit using the brushless motor technology with its 90% efficiency. For more videos like these, check out eeworldonline.com.